ठीक है, आप आ जाइए, मैं जस्ट चेक करेंगे आपको. Sorry. So introduction to this particular programming. So what I mean to say is some people, they want only attend online. So some people, they don't want to attend offline. So certificate will be given to those people who attend online plus offline. That is a rule. So looking at this perspectives, we called each and every person. We make sure that the people are attending and offline and online. However, how many people are attending, irrespective of how many people are attending and other things. So the minimum attendance normally they expected from us is 30. So we have a good response, and in this one, we have segregated into 3 domains. One is additive manufacturing, smart manufacturing, as well as biomedical applications. These 2 manufacturing, we are inclining towards uh, biomedical applications and other things. So we have people from electrical department, we have people from mechanical, we have people from biotechnology, we have people from so many, except computer science and civil, we have many biotechnology people, bioscience and bioengineering. So on we have. So apart from that, just if I give you the statistics, so from Andhra Pradesh, we have 53 applications from where it is subjected to jurisdiction. I mean to say subjected to 100 kilometers radius or something. So we have only taken around 30. Tamil Nadu, we have 20 applications. So we, within the radius, we have taken 10. Telangana, about 10 applications, we have considered 5. Karnataka, 5 applications, we have considered 2. Kerala, 5 applications. We want to consider because their request is coming and again we have considered 1. Subjected to offline also, they are considered. Odisha, we have 2, 1 considered. UP, we have 5, out of which 4 people, they said that they cannot attend offline. So only 1 person confirmed that he is going to come online. So looking at that, we have considered. And from Maharashtra, there are 3. And some people, they said that they have inconvenience in getting permissions from their organizations to attend offline. So on an average, we have 50 people we have shortlisted for attending online and offline. So 50 is the maximum limit of this. And we are hosting them in the next week, 21st to 25th. All the participants, please make sure that you have an industrial tour on 26th, industrial tour on 26th, so that you just kindly book accordingly. If you are already booked, it's okay. But if people are going to book, please book. You have a Indo-MIM tour, which is a world best company in making micro manufacturing and other things. Okay. So with this short notice, I would like to request our Honorable HOD, Professor Madan Mohan, to introduce about the department and tell few words to our participants. Thank you.
Yeah. Am I audible?
Yes, Professor, you are audible.
Yeah. Thank you, Dr. Ravi. So good evening, all. So welcome to this FTP program on smart and additive manufacturing for biomedical applications. So on behalf of Mechanical Engineering and IIT Tirupati, I would like to welcome you all for this FTP program. As Dr. Ravi said, it's like a 2 parts. So hopefully we would like to see you all in next week on campus. So Department of Mechanical and just I would like to give a brief introduction about Department of Mechanical Engineering. So Department of Mechanical Engineering, IIT Tirupati, it started along with the institute in 2015, and at the moment, so we have bachelor's, master's, MS, as well as PhD programs running, and also we have MTech program going on in design and manufacturing stream. And upcoming year, we will be starting on in fluids and thermal. So, so coming to the faculty strength, at the moment we have about 16 faculty. And apart from that, like if you look at each stream, so we have a very strong manufacturing group. 4 people work on that, and 5 in fluids thermal, 2 in robotics, and 5 in solids. So we have a very strong group, and then we encourage industry participation. So as we know, and concerning this today workshop topic, we have Dr. Ravi Shankar, who works in the finishing process, and then Dr. Kiran works in additive manufacturing, and then Dr. Venkaya works in the area of again metrology, and Dr. Ajay works in the area of materials. So this is the core manufacturing group. As we know, I think as you'll be seeing once you are here next week, you can visit our labs. So we are building very state-of-art facilities in manufacturing. So we would be happy to show our facilities and encourage to collaborate with us. So with this brief introduction about the department, I don't want to take much time. So welcome you all for the FTP program. I'm sure that with such a scintillating talks lined up, you will definitely have very fruitful time. And I hope to see you all next week on campus. So thank you.
Thank you, Professor Madan. And now I would like to request Professor Muthukumar, so our Dean Faculty Affairs, to introduce about our institute and few words to our participants. Thank you.
Good evening, everyone. So thank you, Dr. Ravi and Kiran, for arranging such a important, the course, which is of current need. So the additive and, the smart manufacturing, of course, it plays a major role in many fields. Of course, now this particular domain is more or less becoming a kind of interdisciplinary area where you can find application in many, the emerging disciplines such as energy, healthcare, even in even in the agricultural sector, also in many sectors you can find this application. And so this is of, I should say, it's the current importance of the need. So I'm sure that all you the participants will get benefit, and you are going to listen many important and lectures from delivered by various experts. So as per our institute is concerned, IIT Tirupati, we established in 2015. Now currently we are in the third, of course, third batch is already graduated. Now we are in the fourth BTech group. And we are roughly about 1,500 students in the campus. And we have, in addition to BTech program, we have the MTech and MS and PhD program and, MSc programs as well. And soon, of course, we are planning to, add a few more departments. Currently, we have 5 engineering and 4 science background, including HSS. And soon, of course, we are planning to have the interdisciplinary energy center also, where the additive manufacturing also going to play a major role. And plus, maybe in the upcoming years, we are going to add few more departments. So this institute, our institute is among all Tier 3 IITs. We are, of course, making significant progress and contribution to our country's science and technology. And this institute recently, of course, introduced in the NRF ranking. In the beginning itself, we made a big impact in the ranking, and we placed in the 56th position in the beginning itself. And eventually, maybe in about 3 to 4 years' time, and we are planning to reach much better positions in the upcoming years. So about this course coordinator is concerned, Professor Ravi and Kiran. Both they are dynamic, very, very dynamic. And I should say, all you participants, you must get inspiration from these two young researchers. And you can see in our department, majority of the PhD students and majority of the projects are with them, and both are very dynamic and hardworking. And they are arranging many such courses in addition to handling the regular academic. And we are really, of course, thankful to Ravi and as well as Karan for taking lot of interest and in promoting in organizing such kind of course, and also making our institute visible to the public. And so of course we need such kind of programs, then only we can do better in the outreach activities. So the course, of course, I hope, Professor Ravi has given outline about this course. It is going to be organized both in online and offline mode. So maybe once the online mode is over, then you people will be visiting here, and you are going to see many of the state of facilities. And Ravi is having many these 3D printers and many these state of art these facilities. All these things will be going to be a kind of experience, very good experience for you people. And in addition to that, the industrial visit also will in enlighten, definitely will enlighten all your knowledge and add up more you can say the technical content to this course. So in overall, I'm sure that you are going to enjoy this campus. Our campus is coming up really well. Almost you can say 80% of our activities or construction activities are over because of the rain, and I mean some things are got delayed. Hopefully by December end, we will be moving to our new campus. And maybe you can when you come here, please you can go across, you can go around the campus and you can enjoy. Now the climate is really good here. Maybe by next week, hopefully the rain will come down so you can have a wonderful time. And so in addition to now attending this course, and you should also, of course, take forward in many things. And all participants, what we expect from this course is, you have to learn the things, whatever the information you want to learn, you learn and disseminate to the right forum. And particularly the participants who is having only MTech, degree, you try to register for PhD. And we have excellent facilities here, not only in this IIT, even whichever the IIT is comfortable. You guys try to do PhD. Then only, of course, it will be good for for you to survive in the teaching and research career. So with this short note, once again on behalf of IIT Tirupati, I welcome you all for this program, and I hope you are going to have a great learning experience. And once again, I thank Dr. Ravi and Kiran for arranging such a wonderful, you can say very important course, and of course, and taking interest in and continuously taking interest in organizing many such events. Thanks a lot.
Thank you, Professor and Dean, Faculty Affairs. So, before I ask Professor V.K. Jain to speak to the people, Professor Jain, sir, you are available, sir?
Yeah.
Yeah. So let me tell about the speaker, sir. Just Professor V.K. Jain is going to be the inaugural speaker today. He is going to talk about manufacturing vision for future. So he will talk something about additive manufacturing and smart manufacturing, followed by Professor Ram Kumar from IIT Kanpur. He will be talking about additive manufacturing for biomedical applications. Next, followed by Professor Sriharitha. She is from IIT Gandhinagar. She will be talking on bioceramics and other things. Professor Naresh is from Sri Chitra Tirunal Institute of Medical Sciences and Technology, which is a DST, where he is going to talk about 3D bioprinting of organs and other things. So again, we have the fifth speaker, Professor Vimal Katiyar, who is going to, from IIT Gauhati. He is going to talk about biodegradable implants once you place inside the body. And Professor Vikramjit Basu, he is currently at Germany. So he will be coming online because he was expected to be offline, but he says he's in DAD fellowship and he's on currently at Oxford. He's in Germany, but he is visiting Oxford for this week. And he says he can come online, and he is from ISC Bangalore. He is going to talk on bioimplants and translational research. These are the 6 online speakers that we have. This is the information for the Honorable Faculty Affairs as well as HOD. So with this, and I would like to request Professor V.K. Jain, sir, to speak few words to our the fraternity, including us as well as to the participants. Professor V.K. Jain.
Can you hear me?
Yes, sir. Yes, sir.
So good evening to all of you. First, I would like to thank Professor M. Ravi Shankar and his team for inviting me for this inaugural program of this short-term course on additive and smart manufacturing. I believe that such short-term programs on the latest technologies like additive manufacturing, smart technology should be very useful for the organizers, speakers, as well as participants. The important aspect of such programs is that after the participant gets exposure for about a week or this is the program for 2 weeks, both participants and organizers should be able to and should be willing to float offer such courses to their undergraduate and postgraduate students in their respective institutions or universities. Because this should be the basic objective of such program, and I believe that is the basic objective of the government of India as well. I hope some teachers and students would start the research activity also. I always emphasize on this aspect that if you are working, if you are teaching a certain type of the course, as a teacher, especially from IIT, should involve in research and development activities. Because if you go to Google and try to find out top ranking 10 universities, most of those top ranking 10 universities, they were private institutions. And they became top ranking because of their R&D activities. In 21st century, we have a highly competitive world. I strongly feel that you as a nation cannot become economic leader unless you are in the forefront of research and development activities. Unfortunately, in my opinion, Mission 2020 of our ex-president of India, late Dr. APJ Abdul Kalam, and present mission of Government of India, Make in India, cannot be a success unless India pays special attention on R&D activities, R&D budget, and R&D expenses. Why I am saying this? Let us see some facts and figures in this regard about R&D budget expenses of India. At present, China is at number 1 with respect to R&D budget as US $553.4 billion per year. USA at number 2. So you can see USA is at number 2, not at number 1, with US $511.1 billion. And India is at number 6 with US dollar only $66.5 billion. Further, if you see the percent of GDP as R&D budget, Japan is at number 3, which spends 3.2% of their GDP, while we in India spend only 0.9%, 0.9% of our GDP. Now, you can compare these figures and think of expectations in these two missions, that is the Mission 2020 and Make in India honestly. Further, it is not only R&D budget, but also you also need honest, sincere, hardworking researchers and scientists who have junoon or passion towards their goals, objectives. It is only you, the young researchers and scientists, who can make these two missions to succeed. Now, let us see the industrial revolutions. In reference to smart manufacturing, which is the theme of this short-term program. The first industrial revolution started in UK in the middle of the 18th century with the steam engine development. Second industrial revolution took place with the mass production systems in the early 19th century. It was possible by the commercialization of the electricity. The development of ICT and introduction of automation system in the late 20th century can be named as third industrial revolution. The fourth industrial revolution can be named as in manufacturing industries as smart manufacturing, which also includes many areas such as additive manufacturing. I very well remember about 20 years back when I was called by the organizers of a conference at Manit Bhopal to deliver a talk on e-manufacturing. Such e-manufacturing can be named as smart manufacturing. This was about 15 to 20 years back. So this is not a very new subject. People have been working on it. People have been using it for the last 2-3 decades. I will just mention one more incident which I saw when I was in USA. Barack Obama, ex-president of USA, he gave $9 billion for the growth of additive manufacturing in his first term. And he promised that he will give additional $6 billion if he was elected for the second term. And he was elected for the second term and he gave $6 billion additional dollars to the development and growth of additive manufacturing and smart manufacturing. Why I am mentioning this? Because this tells us that if the nations are sincere, they are spending enough R&D, enough fundings on R&D activities, definitely they can do wonders in different areas. And I think about the introduction for smart manufacturing and additive manufacturing, I will talk during my lecture. And lastly, I once again thank the organizers for sharing some of my views about the smart manufacturing and additive manufacturing. Thank you very much.
Thank you, sir, for your nice words and for the encouraging words, as well as your experience wherein you brought in a lot of things. So now it's to Professor Kiran, who is our co-coordinator of this FDP, to give vote of thanks so that we can start the next session, sir. So, Professor Kiran.
Yeah. Good evening, all. Let me introduce myself. I'm Dr. Kiran, Assistant Professor in the Department of Mechanical Engineering, IIT Tirupati. So I feel honored and privileged to get the opportunity to propose a vote of thanks on this special day. So on behalf of the organizing committee and Department of Mechanical Engineering, IIT Tirupati, I convey my regards and hearty thanks to all the eminent speakers who accepted to give their insights in the area of research related to this theme of this workshop, as well as the participants. And I'm also very much thankful to AICTE for the financial support to organize this FTP. And I would also like to thank the organizing team, staff members, and student volunteers who put a lot of efforts into organizing this FTP. So, and also I thank our director, Professor Satyanarayana, for this continuous encouragement in organizing this event. So thank you. And we also want to see your active participation in the coming days during this offline work, this offline participation in this present workshop. So with this, I would like to forward the baton to Dr. Ravi Shankar to perform the drills. Thank you.
So thank you, Professor Kiran. And so with this, I am very thankful to Honorable Director Sir again, because he unable to attend because he has some other commitments. So hopefully we have the opening ceremony on 22nd, basically. 21st it is starting. Our director is again busy on 21st. So we will have the opening ceremony preferably on 22nd. And so on. You can meet our director and other deans. So at this moment of time, with already we have spent some time. So I would like to thank all the people who, please, as Professor Kiran already stated, that please make it useful, because these presentations, whenever you talk about, see, there is a one saying in Africa, I don't know about so whenever somebody happens something or leaves this world or something, then there is a big dictionary will leave this country. That some saying is that we exactly, I don't know the word. So I mean to say is that Professor V.K. Jain, let me introduce about Professor V.K. Jain. Anyhow, I'm a student, so I may not require his things, but still, okay. So Professor V.K. Jain, so I have a lot of fond memories with him. So I hope he is also having a lot of memories, definitely, because whenever somebody comes to him, he will say, okay, I used to have Ravi Shankar and so on. Okay. Okay. So let me introduce, give me one moment of time. Just I am opening the file, sir. So thank you. Yeah, I would like to introduce. Before that, I said, no, I am having a lot of interaction, almost all about 10 years of my stay at IIT Kanpur. So I'm just introducing formally Professor V.K. Jain. Professor V.K. Jain is passed his BE from MACT Bhopal under Vikram University, Ujjain in 1970, ME and PhD from University of Roorkee, which is now IIT Roorkee, in the years 1973 and 1980 respectively. He has 47 years of teaching and research experience. He has served as a visiting professor to University of California, Berkeley, USA, and University of Nebraska at Lincoln. He is retired professor and HAG from IIT Kanpur, and he also served as the faculty at other Indian institutions also. Professor Jain has won 3 gold medals, 2 silver medals, and best paper awards as recognition to his research work. Dr. Jain has written 9 books, including editing books, and 16 plus book chapters published by international and national publishers. He has been awarded Lifetime Achievement Award by AMTDR, which is a prestigious conference. Those people who are attending and belongs to manufacturing and mechanical engineer, you should try to look at if you don't know about AMTDR. And he is one of the NAC member, National Advisory Council member. Professor V.K. Jain is presently editor-in-chief for 3 international journals, one IJP Tech and JAMS and JMF, and associate editor for 2 international journals. And he has worked as a guest editor for more than 22 special issues of different international journals. He has been opted as a member for editorial board member for 12 plus international journals. Professor Jain has guided 20 PhDs, one of them is me, and 100 plus MTechs and MEs, and 30 BTechs and BE students while working at different universities during his career. He has 400 plus publications to his credit, and he has 13 Indian patents and 1 USA patent to his credit. With this brief introduction, I would like to invite Professor V.K. Jain to start his lecture. So, Professor V.K. Jain, sir.
Can you hear me, Professor Ravi?
Yes, sir. Yes, sir. We can hear you, sir.
Thank you, Professor Ravi Shankar, for introducing me so nicely. I have already retired from IIT Kanpur and I have settled down at Bhopal. Now today, I am going to talk to you about manufacturing vision for future. And I don't know how much time I get, but I will try to introduce some latest things regarding smart manufacturing, additive manufacturing, and nano finishing, depending upon the availability of the time. Now, Ravi Shankar,
Sir, बताइए sir.
can you start this PPT? It should move now?
You can move, sir, the cursor. Just you keyboard चलाइए.
Okay. Now, welcome to the course on additive and smart manufacturing, being organized by Department of Mechanical Engineering, Indian Institute of Technology, Tirupati. I am going to talk to you regarding manufacturing vision for future. Organization of the talk is something like this: introduction to manufacturing vision for future, keen observations and ideation, classification of micro manufacturing, two major issues of futuristic manufacturing. What is micro machining? Applications of advanced micro machining, applications of 3D printing, and then application of advanced micro machining. Then next comes to the application of micro casting, micro forming. I am not going to discuss it. I am going to discuss about nano finishing. And then conclusions. Let me do if I can put it here. This should go down, I don't know. Anyway. Now there are certain books which I have edited, I have written, and major part of the talk, today's talk, you can find into that, like Introduction to Micro Machining, Advanced Machining Processes, and then you have the Nano Finishing Science and Technology published by CRC Press, USA. You have Micro Manufacturing Processes, and then you have second edition of Advanced Machining Processes, Machining Technology, and finally, this is the latest book that has appeared in the month of September, published by CRC Press on Advanced Machining Science. Here I have tried to emphasize on the scientific aspects of non-traditional machining processes. Because most of the people, they are talking about the only technology aspects, but here scientific aspects are being discussed. Now, to fulfill your ambitious dreams, be honest, sincere, hardworking, and you should have the genuine towards your objective. Now, see, in my own lectures, especially on the conferences, I try to emphasize that you should have very keen observation to be a good scientist. Just like I will give you some examples of this, like Sir Isaac Newton. An apple fell on his head and he started thinking why it did not go into the sky, why it came to my head. Such a simple incident. But as a result of this, he was able to develop what is known as theory of gravity. Dr. C.V. Raman from India, traveling to England, London, in the ship, and he saw the water of sea as bluish in color. And he started thinking, why it is bluish in color, why not white, why not black? And he developed what is known as Raman effect, on which thousands and thousands of scientists are working on it. That Mr. Ramanujan, a mathematician, he was just 12th class pass. He was invited by that time very famous professor of mathematics, Hardy, and people are still working on these number theories and other things. And all expenses of Mr. Ramanujan were borne by Professor Hardy, living in England, and he died at the age of 32 years old. Now, I am sure all of you know Arc B. And he had a junoon towards his work. That's what I am trying to show. And he was asked by his queen to find out in a crown whether it has gold only or something is mixed. While he was taking bath in a tub, he started feeling lighter, and he realized the principle of physics, Archimedes' principle. And rain on the road, naked, you can see him shouting, Eureka, Eureka, Eureka. And Hawking, Stephen Hawking, now who worked on theory of relativity, quantum mechanics, etc. And the whole of his life, most of the part of his life, he spent on the chair only because he could not walk independently. And he gave very good theory of the means challenges to the existing theory of relativity and quantum mechanics principle. So the question is it necessary for the tool to be harder than workpiece? Who are the engineers? Those who are not engineers, to them I will like to say that cutting tools should always be harder than the workpiece. But is it necessary all the time? You see here, this is a pulley made of cast iron, which was very rough when it was purchased new. After a year, while pulling the water with the help of a rope, it became smooth. My question to all of you is, how it became smooth? Can the rope remove the metal? Metal is much harder than the rope. So, can the rope cut the metal? So, you should find the solution for it. If you can, it is very good. You should try to find it out. Now, I am going to give you introduction to R&D activity, industrial revolution, smart manufacturing and additive manufacturing. Some part I have already told you in my inaugural address, so I will just skip that part from here. And then I will also talk about keen observation. Some examples I have already given to you about keen observation and ideation. This also I have already mentioned to you. There is no substitute for hard work. Economic growth of any country is a function of R&D activity of that particular country. And I have already told you in my lecture, in our lecture, that how China is the #1 country in the world in manufacturing and spending maximum dollars in R&D activity. This I have already talked to you. In my opinion, Mission 2020 of ex-President of India and Make in India cannot be successful unless we pay special attention to the R&D expenses. Now you can see the here map. Here China is at #1 with $553.4 billion. United States $511.1 billion, and India is $66.5 billion. I have already mentioned to you that a country cannot be economic leader unless they are in the forefront in R&D activities. Industrial revolutions I have already mentioned to you. Now, let us see the industrial revolution in reference to smart manufacturing, which is the theme of this short-term program on additive and smart manufacturing for biomedical applications. So all the 4 revolutions I have already mentioned to you in my inaugural address. Can anyone suggest me how to put it down?
Sir, क्या चाहिए, sir?
This line is coming. I am not comfortable.
No, we cannot see any line, sir. You can go ahead.
But I am seeing it. It is creating problem.
No, आपका वीडियो बंद कर दीजिए.
हैं?
आपका वीडियो बंद कर दीजिए तो चला जाएगा कभी-कभी.
अच्छा, okay.
अभी आ रहा है सर?
Anyway, let us see. What is additive manufacturing? Because the main theme of this short-term program is additive manufacturing. Before I talk about smart manufacturing, let me tell you an interesting incident that took place about additive manufacturing. This I have already mentioned to you about the Barack Obama, so I am not going to repeat it. The question is, what is smart manufacturing here? Production of tomorrow's smart manufacturing. Smart manufacturing includes two basic layers: manufacturing equipment layer and cyber layer. They are linked by the interface. Manufacturing equipment has its own intelligence, while the system-wide intelligence is provided by the cyber layer. So this you have to keep in mind. Now, smart manufacturing has been inspired by the concepts of largely developed in the realm of computing, though manufacturing will continue benefit from these concepts and other ideas that will emerge, like quantum computing, cloud be a major disruptor. Smart manufacturing has its own identity captured in 6 pillars that are as follows. Pillar 1, manufacturing technology and processes. 2, materials. These are all parts of smart manufacturing. Data, predictive engineering, sustainability, and resource sharing and networking. So these are the 6 different areas which are known as 6 pillars of smart manufacturing. What is or what are most smartly manufacturing products? Now here is very important question, because I have come across some papers and some people who are working on this, what is known as most smart manufactured product. Now, I don't know whether you can think of or not. If you see the human body or creature's body, animal's body, or insect's body, how they are being made, don't you consider it as most smartly manufactured products? Think about it, because some people have already started working on this aspect, and this may be completely new aspect to incorporate some of the things in your real life manufacturing. We will talk about it, because human body, it has bones, it has flesh, it has nerves, it has teeth, it has eyes, all are the different materials, and they are being manufactured or they are being made automatically or smartly in human bodies or creatures' bodies. So can you really link such kind of manufacturing with your physical manufacturing that you are talking about as smart manufacturing or additive manufacturing? This is just a question for all of you to think about it. Or can you really make use of some of the concepts in your real life? Don't consider it as imaginary question or imaginary thing. People, they are scientists across the globe who are working on this particular concept of most smartly manufactured bodies of the creature, say human bodies, animal bodies, and so on. Next, National Institute of Standards and Technology, which is an agency of the US Department of Commerce. It defines smart manufacturing as fully integrated and collaborative manufacturing systems that respond in real time to meet the changing demands and conditions in the factory, supply chain network, and customer needs. Now, please be careful while we are talking about smart manufacturing, and please see here, it meets the changing demands which are changing continuously, and conditions in the factory, supply chain network, and customer needs. It cannot be something fixed that you have fixed and it is going to work on it. It has to be responsive. It has to respond to the changing demands of these three elements. In other words, it means that the active manufacture-based technologies and systems that can respond to complicated and diversified situations of manufacturing field in real time. So it is really working in real time, and it has to respond the complicated and diversified situations of manufacturing, which includes the customers also. As we will see, supply chain as written over here, that includes the customers needs over here. The major technologies are IoT, Internet of Things, CPF, cyber physical system, cloud, etc. The R&D programs related to manufacturing focus on key technology assignments, including IoT, big data. Wherever we are talking of automation or smartness, you have to have very big data. Data analytics, CPS, system integration. Integration plays very, very important role in integrating all these different elements. Sustainable manufacturing. I will talk about sustainable manufacturing in detail little later, and additive manufacturing also I am going to discuss about. To respond aggressively to the innovative manufacturing environment change. And this is called as the fourth industrial revolution also, which I have mentioned earlier. So smart manufacturing, additive manufacturing, they come under the fourth industrial revolution. So now the question is, as I mentioned, I talked to your organizers also, and I asked them that whether participants are involved in R&D activities or not. And I believe most of you are involved in R&D activities, and that's why I have deliberately written some research areas in smart manufacturing are as follows. Sustainable manufacturing, which I mentioned to you a little earlier, developing production systems that can increase resources efficiency and reduce the emission of environmentally hazardous substances. Now, I am sure all of you know that every country is working on sustainable manufacturing because of environmental problems. So hazardous substances through green design, the use of environment-friendly materials, and the optimization of the production processes. So these all the three are very important: environment friendliness of the materials, optimization of the processes, and the green design. Then only you can call it as sustainable manufacturing. Second one is additive manufacturing. The method of applying 3D printing technologies to the manufacture of components and products. There is a difference between the component and the product, which can reduce time and cost for product development and manufacture. A lot of scope of research activities in theoretical as well as experimental work is there as long as additive manufacturing is concerned. My suggestion will be that please don't just try to spend your time in the making the product or just developing a technology only. Try to go into the scientific aspects of additive manufacturing. Try to improve the theory so that you can improve the additive manufacturing processes as such. Then Internet of Things, embedding sensors and communication equipment in manufacturing, machinery and lines, big data and data analytics. So these are the certain areas, and I'm sure some of you may be involved in these ones, like cyber physical system and system integration, and then data interoperability. This is another important area where you can work for your master's program, PhD programs. Continue. Multi-scale modeling and data interoperability. And then comes the intelligent automation. This is very important as long as automation is concerned, because it controls many things, including the process time or process efficiency. And then scale-level and multi-level cyber security. So these are some of the areas where you can do your research activities if you are involved in smart manufacturing. So it is not, as you can see, there are 7-8 areas or more than that, and they include different disciplines, not only manufacturing, computer science, materials, data analysis, and so on. So you can choose the area whichever you are expert, and still you can work in the area of smart manufacturing. Now, let us come to the conventional manufacturing or general remarks, classification of manufacturing, miniaturization, and sustainability. Types of manufacturing, quantity point of view. I am sure most of you know it. That is known as job shop production, batch production, mass production, flow production. Then size point of view, you can have macro production, meso production, micro production, and nano production. Then you have process point of view, like subtractive process, additive process, mass containing process, joining process, etc. Now, you have the different processes for each category, for these ones as well as for these ones. Because same process cannot work in most of the cases for mass production and job shop production. So selection of a right kind of the process, like macro, meso, micro, nano, you will have to select different type of the process for different type of the manufacturing. The question is, why miniaturization? Because if you recall, 30, 40 years back, what was the size of the telephone? Now, you see the size of the mobile, which is not just a telephone only. It is calculator, it is computer, it is newspaper, everything is there. So all this is possible because of miniaturization of the different products, and definitely certain technologies are being developed for that purpose. So what are the advantages of this miniaturization? Let us see. Less material consumption during manufacturing, low energy for device excitation, lightness and portability, increase of selectivity and sensitivity, cost performance advantages. All these are the certain minimum advantages that you get from miniaturization. And for miniaturization, while you are making miniature products, you come across what is known as micro manufacturing. So micro manufacturing has received great attention of researchers in the recent years. Nowadays, it is getting a lot of publicity and attraction, both venture capital and federal government, central government research support. It has also opened up various kinds of new interdisciplinary research areas. What is micro manufacturing? Let us see the definition of this. Oh. What happened, Ravi Shankar?
स्क्रीन चला गया,
कैसे?
पता नहीं सर.
क्या किया जाए? स्क्रीन शेयर अगेन.
आगे स्क्रीन शेयर कर दीजिए सर.
Manufacturing. Now there are two major issues of futuristic manufacturing. When we are talking of futuristic manufacturing, one has to take care of these two basic issues: challenges in miniaturization or micro manufacturing, and second is very important, green manufacturing, sustainable manufacturing. Now both these are very, very important issues as long as manufacturing is concerned, and directly or indirectly, almost all countries are worried about these issues. Researchers in different countries. Hello? And if you want to find the solution for it, additive manufacturing, in my opinion, is the solution for it. And I am sure in the coming 2 to 3 decades, many conventional manufacturing processes will be replaced by additive manufacturing. I will show you some of the examples. Please see it carefully. Now here is the electricity requirement, and here are the process rate, means kilogram per hour. Now you can see here there are various processes. Some are requiring very high energy per kg production, and some are requiring low, comparatively low energy per kg requirement. As you can see here, a comparison of specific energy required for various micro manufacturing processes relative to conventional manufacturing processes. This includes conventional manufacturing processes, and all these are the newly developed, advanced or non-traditional manufacturing processes, as I will show you here. Order of reducing energy required. If you see here, oxidation is requiring maximum energy, as this is the oxidation, and second is the drill EDM, then there is the sputtering, then CN tubes, CVD, dry etching, wire EDM, grinding, and so on. So what I am trying to show here is that selection of a right kind of manufacturing process or machining process is very important. Because if you don't select a right kind of the process, then energy consumption may be very high, although the same thing you can obtain with the low energy consumption also. So this is very important, and this is mainly for green manufacturing people. Comments. Commonly used processes in microfabrication are having very high value of electricity requirement, because latest technology which are used commonly for microfabrication or micro manufacturing, their energy requirement is very, very high, as we have already seen, like CVD, etching, etc. It indirectly indicates non-friendly to the environment, as I have shown you in the earlier slide. The processes which require comparatively low energy per kg production are conventional machining, conventional finishing, casting, grinding, etc. Manufacturing process selection criteria should be based not only on energy requirement and cost, but also environment friendliness as well. This is very important point to take care of it. All manufacturing engineers, scientists and researchers, they should take care of this environment friendliness of a particular manufacturing process. Some environment friendliness sustainability index should be developed as a guideline for evaluating different micro manufacturing processes for different types of production. This is a new idea. People have been working on it, and I suggest some of you should think about it to develop a systematic method for sustainability index evaluation of different manufacturing processes. Just as you know, for the evaluation of the life of the tool, you have the tool life in terms of minutes or different processes. Same way, you can try to find out sustainability index of each manufacturing process so that while selecting a particular process, that can be taken care of. Design machines which enable manufacturers to produce goods more efficiently, meaning thereby with less material requirement, less energy requirement, and less waste. These 3 points are very important to take care of while designing the machines. Classification of micro manufacturing processes. Now here, there are various subtractive manufacturing processes like traditional subtractive manufacturing processes, micro turning, milling, etc. Non-traditional subtractive manufacturing like laser beam machining, electron beam machining, and so on. Like additive manufacturing, which includes additive manufacturing AM processes like CVD, PVD, etc. or layered manufacturing also comes under this category. Mass containing processes like casting, forming, and then joining processes. In the last few years, the topic of sustainable manufacturing processes has become important. Machine tool industries require innovation, competitiveness, and sustainability in the selected manufacturing processes. Sustainability requirement of smart manufacturing, key consideration. Because while selecting smart manufacturing process or devices, sustainability should be given due importance. Manufacturing sustainability has 3 dimensions: economic, social, and environment. And all the 3 are equally important. Economic, any manufacturer will give the high priority for economic. They should give high priority to social concern also, and social concern, especially the safety, etc. of the workers or the society who is using it, and then environment friendliness. Increasing the energy resource efficiency of the machine tools linked to social and environmental sustainability goals. So if you are able to increase the energy resource efficiency, then definitely you are able to consider social and environmental issues. Environmentally efficient machine tools, they are profit for both manufacturer as well as users. The user can save on material and energy costs by optimizing production processes, whilst the machine tool builder can gain a competitive edge by offering value-added products at comparatively low cost. It is not true all the time, most of the time, yes. What about additive manufacturing from economic, social, and environment point of view? This is very important to analyze. In my opinion, additive manufacturing fulfills all the 3 requirements of sustainability as mentioned here as economic, social, and environment. Those who are familiar with the additive manufacturing, I'm sure they know it. Three D printing, additive manufacturing, these are the different names, or layered manufacturing. Now, what is additive manufacturing? Just try to see this. Please see this video. Now, as you can see here, layer, here this product is being made, this layer is developed, and this layer is developed, this layer is developed like this. And you should see it, it is layer by layer deposition. Maybe metallic part or non-metallic part, because in biomedical applications, you use both metallic parts as well as non-metallic parts. And additive manufacturing is efficient enough to produce the products of metallic as well as non-metallic parts. Parts useful for engineering as well as biomedical applications. Oh my God, this video is not working. Now you can see here, there are the different joints, etc. of the human body. And most of the organs, they can be built with the help of the additive manufacturing processes. Different organs as per patient's body requirement can be made. Somehow, unfortunately, this is not working. I had, but anyway. Now, 3D printing and future of manufacturing. 3D printing changes the calculus of manufacturing by optimizing for batches of one. This is very important to note that when we are talking of 3D printing or additive manufacturing, the parts being made or the batches are of one only, not very large batches are there. Flexibility to build a wide range of products. It can be done near to the point of consumption. This is very important if you want to make certain things in your office itself. And if you have the 3D printing machine, you can make it there, then and there only. It implies a serious change to supply chains and business models. When the volume of production is low, this technology is used to produce final components without making tools or dies or molds. Now you can think of completely a new concept is there. There is no tool, cutting tool or die, or there are no molds or no patterns. And still you are able to make the product directly. Manufacturers are looking to shorten supply chains, eliminate shipping costs, and reduce lead times. All the three are very important because you are able to make the products in your office or at the place of its use. So you are able to eliminate the shipping cost. Supply chains are completely reduced because you don't need any supplier for this particular case, because you are able to make it at your own place, except that you have to get the supply of the raw materials. And reduced lead time is substantially reduced once you are ready with the software or CAD/CAM software is there. These can come as benefits from additive manufacturing technologies. So these three are main things. Now the question is, with this 3D printing and future of manufacturing, where are we leading to in additive manufacturing? Modern manufacturing could be done without a factory. Can you think of manufacturing without a factory? But it is possible in case of additive manufacturing. Could you think of manufacturing without cutting tools, without factories, without machine tools, without production lines, without economies of scale, means mass scale, mass production, batch production, and so on, without tooling? Because any kind of production you take, casting, welding, cutting, etc. Everywhere you need the tool. Assembly lines and supply chains. So without these things, can you think of manufacturing or production? But it is possible with the additive manufacturing. However, this is exactly what is happening as 3D printing reaches individuals, small businesses, and corporate departments. 3D printing, e-manufacturing is the futuristic of manufacturing, because as I mentioned in my first inaugural address also, that in after 3-4 decades, many of the conventional manufacturing processes will be replaced by additive manufacturing. Now you can see here, this test part represents engine component which GE, General Electric of USA, hopes to make by additive production or additive manufacturing. This part faces performance demands, including thermal cycling loading across a dramatic temperature. This is subjected to a very high temperature of 1000 degree or more than 1000 degrees centigrade. Challenges are there. This is the first GE aviation additive part which they made. If run at full production today, see, it is talking about the futuristic requirements of additive manufacturing. So GE, General Electric says, GE would consume most of the direct metal laser sintering capacity currently available for production use in North America, that is USA. So GE says that its own requirement will be so much that whatever are the machines producing in USA at present, all of that can be consumed, all those products can be consumed by GE alone. So what you need? This is the very old example to show the capabilities of GE, sorry, capability of additive manufacturing. Things have changed substantially after this. That is why GE company says, this is very important to note, one of the two advantages will have to be happen, one of the two advances have to happen in the next few years. Either the number of additive manufacturing machines available for production in North America will have to increase, or machine technology will have to improve to the point that the machines coming into use are much faster than the machines in use today. What they were suspecting is that the requirement in future will be so much that the existing machines and capability of the existing machines will not be sufficient. Or indirectly, you can say that additive manufacturing technology, machine tools need very high R&D activities to meet the requirement of USA and other countries, because they can see the advantages of additive manufacturing. Now this gentleman, 3D printing mini jet engine. This is developed with the 3D printing, and it can run at 33,000 RPM, this particular engine, because they work basically on aerospace industry. Additive manufacturing grows parts directly from a CAD file using layers of fine metal powder. This metal powder can also, there can be non-metal powder also, and an electron beam or laser beam. The result is a complex and fully dense part without waste and manufactured in a fraction of time that it would take using other methods. Now, there are many biomedical applications of 3D printing. How to build customized parts quickly and flexibly. This is very, very important. Here, the word customized part is very important as long as biomedical applications are concerned. Conventional processes are often costly, time-consuming, and technically highly complex. 3D printing for dentistry, a flexible mode of manufacturing. It produces hundreds of individual dental crowns in one batch. It offers a continuous competitive edge. 3D printing for orthopedics. The patient's individual anatomy is the key factor. This is very important. Patient's anatomy. Because as I keep telling all the time, that it should not be something like the Bata shoe, that you have 8 number and you have 9 number shoe. There is nothing like a 8.25 number or 8.5 number or 8.75 number. But patient's anatomy may require that kind of the parts. And each patient will have different anatomy, different sizes and shapes of the part. And you can fulfill that kind of requirement by additive manufacturing. Means you can customize the production of the parts in case of 3D printing, which is otherwise not so economic and not that much possible. Meeting the patient's specific anatomic needs reduces hospitalization time. It reduces problems normally caused by ill fitting of the implants, as I gave you the example of 8.5, 8.75 or 8.25 size shoe. It reduces healthcare costs, something like Bata shoe, as I just told you. So the solution for this is additive manufacturing only. Now here you can see application of 3D printing, full scale reconstruction by a 3D printing technology. This was the, head was joined by 3D printing in China. This baby head was joined by 3D printing. It was growing like anything, and they replaced it by 3D printing. And now the baby is growing in a normal fashion. Earlier, it was not so. So this was possible by 3D printing. As she continues to grow, that titanium implant, which they have replaced here, will become surrounded by her own bone, which will lead to strengthening of the top of her skull. She is expected to make a full recovery. Now, these are some of the examples which have been developed with the help of the 3D printing. The Vienna University of Technologies 3D printed race car, approximately 285 micrometer long. The total length of this car is 285 micrometer, that is 0.285 millimeter, was printed in a 4 minutes. This was developed, printed in 4 minutes. It demonstrated that high speed, ultra precision 3D printing is possible. Also depends on lower areas such as medicine. You can see here 3D printed structures. This is the kidney, top left, ear, top right, and then fingers. So they are printed with the help of 3D printing, or developed with the help of 3D printing. They can one day help address the organ shortage and the need to repair, if not replace, damaged body parts. Now this is another example. The 3D printed metal leg that is here. Cover on this prosthetic leg is delicate yet strong and reflects the wearer's individuality. Means it was made according to the leg sizes, dimensions of this particular patient. There are plans to 3D print the car's interior. Now you can see here, these are the different parts developed by 3D printing. 3D printed adjustable wrench over here, this was developed in one go. Not that different parts were assembled later on. It does not require any assembly. This is 3D printed metal gear developed in one go. This I have already shown to you how 3D printing works. You develop layer by layer, one over the other layer like this, and finally you get the product like this. All these products have been developed in one go only. They are not assembled. 3D printing, also known as additive manufacturing, builds objects layer by layer that we have seen over here. They are developed layer by layer. Traditional manufacturing typically uses a subtractive process for developing such kind of thing, like I told you earlier, milling, turning, drilling, etc. But here, those processes, all those processes are replaced by printing. Process whereby materials are cut, ground, or molded to create an object like this. Here you will require a lot of assembly in conventional processes. Now another process which is very similar to 3D printing, that is focused ion beam deposition, which is layer by layer deposition at nano level. Please note it carefully. FIB, that is also known as focused ion beam FIB deposition. It is basically good for nano fabrication. Even micro fabrication becomes quite large for it. Now this is the coil, 700 nanometer pitch, 80 nanometer line width, diamond-like amorphous carbon fabricated by FIB induced deposition. It was done at IIT Kanpur Physics Department. And here is the microwine glass with 2.75 micron external diameter and 12 micron height. So all cross sections in nanometer, these are the different rods or pillars in nano size. They have been developed by deposition in certain labs. Radial DLC free space wiring grown into 8 directions. You can see over here, and see 8 direction and 16 direction. And this is taken from this particular paper. Now, Dr. Ravi Shankar. Hello.
Yes, sir.
Should I continue?
Yeah, sir. Please go ahead, sir.
Okay.
You have another 30 minutes.
So I am not going to discuss the principles of advanced machining processes. I am just going to talk about the applications of certain interesting applications of advanced micro machining processes, especially micro nano finishing. Some applications are given over there. This nano finishing or micro finishing is required, and it is known as post processing after fabrication of the component using either by machining process or 3D additive manufacturing forming, costing, casting, welding, etc. After these processes, you require final process as the nano finishing or micro processing process, or even after treatment. So most of the work presented here has been done at IIT Kanpur. Whatever slides I am going to present, they are reflecting the work done at IIT Kanpur. What is micro machining? First thing is, what is micro machining? There can be different definitions. So many definitions are floating around as long as micro machining is concerned. Micro plus machining, that is the removal of material at micro level, because micro plus machining, that clearly tells that you are removing the material at micro level. Unfortunately, the present day notion is machining of highly miniaturized component with miniature features. Literally, it is not correct because we are talking about micro machining. So where micro word is there, which tells less than 1 millimeter. So wherever you are creating the feature less than 1 millimeter dimensions by machine, removing the material less than 1 millimeter dimension, then you can include it in micro machining. So literally, more correct definition is material removal at micro nano level with no constraint on the size of the component. Just hold on for a minute. Sorry for interruption. So with no constraint on the size of the component, for example, macro, meso, micro, nano. Some examples are like MEMS or NAMS. So this is the definition which I believe should be, although there are certain definitions which are different from this, especially the CIRP and others, they have taken, certain component is smaller than 400 micrometer or so that come under the micro machinery. But I am not going to go into details of those. Now you can see here, like this is a component. This is the 2 millimeter by 2 millimeter size, and you can see what are the different, how many different components are there, and this is the leg of a housefly. So you can imagine the dimensions of these components, and all of them are prepared by micro machining process. Pattern of holes drilled by electron beam micro machining. So these are the holes which are developed, see, especially in case of food industries or fabrication or fiber industries or clothing industry, they need the filters of very fine sizes. Textile industry, here are the holes which are prepared by electron beam micro machining of 0.09 millimeter, that is 90 micrometer. Holes density 4,000 holes per centimeter square. Stainless steel is the workpiece size and the thickness is 0.2 millimeter. And time taken per hole is 10 microseconds. But industry people of textile or food industry, they are not happy. They say this is quite large size holes of the filter. So people develop the hole size as 6 micron. Here it is 90 micron. They developed 6 micron size holes and hole density as 200,000 holes per centimeter square. Thickness is 0.12 millimeter and time taken per hole is about 2 microseconds. So you can imagine the miniaturization of the holes that is required in certain industry. And latest technology or advanced machining processes are able to meet those requirements. Now you can see here, This is the, if I ask you to write your own name on your hair, I'm sure most of you will say, no, it is not possible. But here you can see here, excimer, E-X-C-I-M-E-R, excimer laser. This has been written on the human hair. And you can see the clarity of the letters shown below over here. And this has been done with the help of laser beam micromachining process. Micromachined letters on a single human hair. Note the clarity of the letter in the closing view. Now you can see here, this is the micro components, enlarged view of the micro component. This is further enlarged, so you can see different parts over here. So this is a microfluidic mixture is developed over here. Its enlarged view is here. So you can see here, this works as the mixture, microfluidic mixture. Now this is the 520 micron diameter extrusion die over here. And this is the ladder with 100 micrometer gap between the teeth. These are the teeth, this is the 100 micrometer gap. And here are the pin over molding jig. These are the pins of 655 micron holes. And this is the micro gears of 520 micron size. And this has been prepared, all these products have been prepared with the help of wire electric discharge micromachining or electric discharge micromachining process. Now this work was done at IIT Kanpur by one of our master's students. This is the fabrication of micromixture by electrochemical micromachining process. Micromixture applications of electrochemical micromachining. Now you can see here, this is the mixture over here, and this is the black ink coming over here, this is the water coming over here, and after mixing, these are the two different fluids. After mixing, they are looking like a single fluid over here, mixed fluid. Now machining of complex shades workpieces, very important. Now this is the turbine blade. Earlier turbine blades used to have micron holes for cooling purposes, but nowadays they want the turbulated holes like this. This is the hole around 1 millimeter or less than 1 millimeter diameter, and across the walls they have the other holes, so that the cooling becomes more effective. Now how will you do it? Very difficult task, because this diameter itself is around 1 millimeter, and you have to drill the hole across the wall. So this you can use as electrochemical micromachining process over here. Now this is the actual photograph of the work done at IIT Kanpur, and you can see the continuously varying diameter micro holes developed in the turbine blade. Now this is the comparison of the actual profile obtained, and this is the predicted profile. Both are compared over here, and this is the actual photograph. Now this has been done. This has been prepared by, this can be prepared by ECM, wire ECMM or wire EDMM. This is prepared by wire EDM, electric discharge micromachining process, and this part has been taken out from here. And the difference between these is a few micron size. Outer diameter of this and inner diameter of this, it varies by few microns. Now, very important here, this is a cylinder which is having hundreds of holes, and the surface finish of these holes affects the performance of this particular cylinder. So, how to finish it? So, this has been finished. This has been finished using the nano finishing process. You can use it, abrasive flow finishing process, or other processes also. So all the hundreds of holes are finished in one go, and that surface finish can be controlled with the help of the size of the abrasive particles, viscosity of the medium that you are going to use and the forces or the pressure that you are applying on the medium. Now, this is the example of how to do deburring inside the two meeting surfaces with required surface finish of this job. This is the IC engine part, and they are the intersecting surfaces here. And now the question is how to finish them, how to do the deburring of those parts. Here you can see here, these parts are there, but this is going through parts and then intersecting surfaces are there. So burr removal and finishing is the problem. This engineer is thinking about it. And then there are unreachable places where you cannot take the grinding rods, etc. Internal geometry is complex. Form tools cannot reach there. So this engineer is in trouble and he is thinking how to do it. Then the idea comes of abrasive flow machining process, and he can do it with the help of the abrasive flow finishing process. So material can be removed in the form of small chips, micro nano chips, by random cutting edges with indefinite orientation and geometry with shape changing fall. So that way he was able to finish it, and this was developed by extrude hone, and this is the advertisement which was supported by the extrude hone. Now here you can see abrasive flow finishing setup for knee joint finishing. You can have the knee joint over here. This is the medium, and this is the the device which controls heating, cooling of this medium, because heating or you have to maintain a certain temperature of this medium. Otherwise, the surface finish obtained will be varying. So that you can control with the help of this. Now, IIT Kanpur and CMTI, they had a collaboration in developing the abrasive flow finishing process machine tool, and this is the machine which was developed by IITK CMTI collaboration at CMTI Bangalore. And you can see here, and this is an excellent machine in the sense that it can control the temperature along with other parameters of finishing, and its cost is also comparatively low as compared to the cost of the machine which was being supplied by the extrude hone USA. Now, then there is another process called MRF, magneto-rheological finishing process. Now you can see here, this is the initial surface before finishing, and its surface roughness value, RA value by 1260 nanometer. This is the highly enlarged view, SEM, scanning electron microscope view, 3D view. Now after finishing, this surface finish 1260 nanometer came down to 12 nanometers. So you can compare this surface finish with this surface finish. Now this is how it works. This is the lens which is to be finished. This is the medium which is having abrasive particles and iron particles. And at the bottom there is the magnet. Here is the magnet. So magnetic particles or iron particles are attracted towards this, and abrasive particles are in contact with the lens, and they are able to finish it. And it has been claimed by QED. QED is a company of USA which developed this MRF process, and they claim that they were able or they are able to achieve the surface finish of less than 1 nanometer. The working principle is very simple. Here is the workpiece, as you can see here, and this is the abrasive particle, as you can see here. Abrasive, this is the lens which is to be finished, and these are the abrasive particles. So this is the abrasive particle. It is having shearing force and normal force. Normal force is responsible for its penetration, and shearing force is responsible for removal of the material in the form of micro nanochips. So you can see there is a reduction of surface finish by more than 100 times less. Now, there are two processes, as I have shown to you, MRF process, I have just shown to you, magnetorheological finishing process and abrasive flow finishing process. And both these processes have their advantages, but they have their demerits also. MRF is not suitable for very hard materials, and AFM is not suitable. It is not externally controllable, non-controllable. So what we did at IIT Kanpur, Dr. Sunil Jha, he developed a new process known as magnetorheological abrasive flow finishing process. And the viscosity of abrasive medium in MRAF process can be manipulated and controlled in real time. Hence, it helps in deterministically and selectively abrading the workpiece surface. So the use of machining setup similar to abrasive flow finishing process or abrasive flow machining process will remove the shape limitation on workpiece surface to be finished. So in this particular case, as you will see in the next slide, we have used the abrasive flow finishing setup. I will show you. This is the abrasive flow finishing setup. Having a magnet, north-south magnet, and this medium is having the abrasive particles as well as iron particles or carbonyl iron particles, and motion is being given up and down, and it is able to finish these workpiece shown over here. That abrasive particles, this is the workpiece. Now you can see here, when no magnetic field is applied, they are distributed randomly. Abrasive particles and iron particles are distributed randomly. But when magnetic field is applied, you can clearly see they are properly arranged. Iron particles and abrasive particles are seen over here in the form of line. These are the CIPs, and these are the abrasive, bigger are the abrasive particles, and these are the CIPs, the smaller particles. So when they are moving up and down, abrasive particles are in contact with the workpiece surface, and they are able to finish it. And researchers in our lab, they were able to achieve as good as 10 to 15 nanometer surface finish on the very hard materials. Now you can see here, this is the initial surface finish, initial SEM image of the part. This is the 2D sketch of the surface roughness. This is after 2000 cycles. Initially it was 0.28 micrometer RA value, then it came down to 0.10 micrometer after 2000 cycles. And then after finishing with diamond, this was finished with silicon carbide abrasive particle, this was finished with diamond, and again it is 0.10 micrometer. But you can clearly see the difference between the texture of this silicon carbide finished workpiece and diamond finished workpiece. So it clearly tells that the type of the abrasive particles you are using also makes a difference. Knee joint and its replacement by femoral nano finishing is required, as you can see here, because there is a relative motion between the femoral and other part. So friction plays an important role. Now this is to be finished. This part is to be finished, and it is having the relative motion between different parts of this knee. And as we here also when relative motion is there. So this is the schematic view of this particular one, and this knee joint has been finished at IIT Kanpur by one of the PhD scholar, Dr. Ajay Sitpara, and Dr. Manas Das of IIT Guwahati, Ajay Sitpara of IIT Kharagpur, and some MTech students. A lot of work has been done in this direction at IIT Kanpur. So you can see different parts over here. Now this is the knee joint, femoral, which was finished at IIT Kanpur, and this is the CNC machine, and this is the medium which is going to finish it. As you can see over here, we have achieved 29 to 56 nanometer as surface finish. However, doctors recommend that if it has 100 nanometer, it will work well. Now this is the knee joint, and this is actual finishing it. This is the medium over there. Photograph of MR finishing tool for free form surfaces, and this is the free this one. The close view of the MR polishing fluid. This is the close view MR polishing fluid, and see this is the finishing in action. Orthopedic surgeons suggest 100 nanometer, but we were able to achieve 29 to 56 nanometer surface finish on this particular knee joint, and it was purchased from the market, and these are the kind of the knee joints that are used by the doctors.
So we'll take some questions, sir, now.
Just one.
Sure, sir.
Next
Sure, sir.
slide.
Thank you, sir.
Nano finishing of human implants. Now there are many human implants. All these joints have friction to play its role, some form or other. Yeah, knee joint, hip joint, so many joints are there. So reduced friction will definitely lead to comfort to the patient, longer implant life, and it minimizes the need for the next replacement. So patient's comfort is also there. In this case, nano finishing comes to rescue. Parts may be made by 3D printing, but final operation you will require as nano finishing. With 3D printing, manufacturing can be employed for matching the parts with the individual patients. This is very important, anatomical matching of the implant with the patient's anatomy. 3D printing manufacturing is easily adaptable for minor changes in the size and shape of the part as per patient's requirement. So as I have been told by the organizers, I will stop here. But there are many areas in micro machining and nano finishing where people have been working and they are working for their PhD program and master's program. Now it is open for discussion. You can ask the questions, whatever you need. Hello.
Thank you, sir. Thank you for your elaborative lecture or talk on the manufacturing vision for future. You have given a lot of vision in terms of post-processing of AM and smart manufacturing and so on, which gives overview on some of the future prospects. Now it is open for the questions. People, you can unmute yourself and one after the other, please ask, and I'm sure Professor V.K. Jain will give you the suitable guidance and answers. Thank you. So if you can raise the hand or something, then we can also unmute yourself. Otherwise, you can also unmute. We don't have any restrictions on you.
Good evening, sir. I'm Dr. M. Srinivas Kumar, sir.
Yeah, you can introduce yourself and you can ask, please.
Yeah, I'm Dr. M. Srinivas Kumar, sir, from Nasraopeta Engineering College, sir.
Please go ahead.
Yeah, sir, this 3D printing, as sir has explained very nicely, sir, and the future is with the 3D printing. I hope sir has explained very clearly about the what you call on human organs also future we can develop. Now it is in metal stage, sir. Yeah. For human organs, what materials we have to use, sir?
Pardon, I am not a.
Okay.
I have not heard you.
So, sir, his question is that, so nowadays metal 3D printing people are using, what are the common materials that you can one can use for implants. Am I right, Srinivas Kumar
Yes,
Garu?
yes, sir. Yes, sir.
So what are the materials that 3D printing in metals they're asking, sir?
See, it depends upon which implants you are talking about, right? If you, there are certain materials, exactly I can't tell you, but there are certain materials which are being used, and they may be metallic, they may be non-metallic. Depending upon your requirements, you produce the powder for it, then you have the laser beam or electron beam. With the help of this, you can develop this. Unfortunately, my video is not working. Otherwise, I should have shown you very nice video for this additive manufacturing. So, which material depends upon your, implants, of which material it is made up of. And you can use the biomaterials also for this particular purpose.
I mean, for each material, the conditioning of the machine, I mean, the temperature or cooling requirements.
Yeah. See,
The machine also should be flexible to control all these.
See, depending upon your material and the implant, you have to decide the size of the powder that you are going to use in micrometer or nanometer,
Yes, sir.
and the temperature at which you are going to melt it, and then the deposition and the thickness of each layer.
Yes.
Because thickness of each layer is going to control your final surface finish also. So final operation that you are going to have in the 3D printed part is the nano finishing.
So the machines are also to be customized according to the manufacturing of these parts.
Pardon?
Or the 3D printing machine also to be
Yeah.
customized, sir, for a particular implants. This is the machine and material we have to use. And if you want to change another materials, the machine also to be changed.
See,
No.
Yes, sir.
each machine has its own capabilities,
Okay.
but you cannot say just like a turning machine or milling machine or milling
Yes, sir.
machine. No.
Yeah, right, sir.
3D printing, depending upon if you can prepare appropriate software for it, then it can have motions in all the three direction, X, Y, Z direction, and they can prepare all kind of parts. As I had shown to you some of the parts over there in my presentation, that wrench was there, or those ear was there, or fingers were there. So they are very different from each other, but all of them are made in one go on the 3D printing machine. So you don't require, really speaking, drilling machine for drilling a hole. While making it itself, you are able to create the hole over there.
Yes.
Only thing is that you may not get that kind of dimensional accuracy, which you have to bring it in post processing. Am I clear?
Thank you, sir. Thank you. Very in-depth information was given, sir. Right, sir. Sir, if that video is not working, please share it to Ravi Shankar, sir. When we come to Tirupati, we will see that video, sir. Please.
Okay.
Yeah.
I don't know. Online. Yeah, I saw it on the tablet, laptop. It was working, but while presentation, something went wrong.
Right.
I will try to just, if I can see it.
Yeah. So
Okay, sir.
Yes. Any other question, please?
so any other
Sir,
questions? Yeah, please.
very good evening, sir.
Good evening.
Thank you for Professor Ravi Shankar and Professor Kiran and his team for giving this opportunity to meet a legendary person, Professor V.K. Jain in manufacturing.
No.
Sir, my question is, sir.
Can you give few minutes? Let them see this particular video. This is about the
Sure,
3D printing, and you can see how nicely they are able to make this.
We are unable to
different-
see, sir. You have to share the screen.
Share the screen. Yes, sir.
Is it visible?
No, sir. You have to share the screen.
Oh, just wait. How to?
Again, you can share the screen, sir. Same procedure.
I don't know. Okay, I think it is with you, Ravi Shankar.
Please share the screen, sir. Anyhow, it's okay, sir. Otherwise, just you can give the Google link or something. We can download it. We can show them.
Is it visible now?
It is visible, but video is not visible. You can click on the videos.
Let me start. See. Is it visible?
No.
And not visible?
No, sir.
PPT only visible, sir.
All right. I don't know.
It's okay, sir. It's okay.
You can try if you can show it to them. It's a very good video for 3D printing, and it is showing different shapes and sizes. You can quickly make them. Any other question, please?
So, Professor Naidu, you can go ahead.
Yes, sir. My question is that do we have any commercialized facility which can print dissimilar materials at a time, sir?
Pardon?
Do we have any commercialized facility which can print dissimilar metals at a time, sir? 3D printing, dissimilar metals.
No. Your question is very important, and I asked one question to all of you. What is the most smartly manufactured product in the world? And human body, I gave you an example that
Yes, sir.
it has the bones, it has the fleshes, it has the eyes, all kind of materials are there, and they are developed automatically or smartly automatically. Now, on the same philosophy, what can we have different metals and non-metals working at the same time for the same product? That is the question to be answered by the researchers like you and others.
Yes, sir.
And if I know correctly, it's not that easy. You have to first understand the science and then the technology and then develop the whole process. At least I don't know whether you can do that kind of the mixing of the material to make a product. Any other question, please?
Professor Naidu,
you, sir.
You can do it actually. Sir, there is a concept called 3D printing of multi-materials. Okay?
Okay, sir.
Thank you.
No more question?
Hello,
Yes.
So, Professor,
can I talk, sir?
Yeah,
Professor
please
VK
tell me.
Jain is expert in the area of post 3D. So
Yes, sir.
people can take advantage of post 3D like finishing and other things. He can be more comfortable and more happy to answer.
Yes, sir.
Yeah, thank you. Yeah, please go ahead.
So myself, Dr. Devakar Makreddy.
Yeah.
So I would like to ask question in micro machining, sir.
Yeah, please tell me.
So you said to finishing any material up to 29 nanometer, we got the finish right on the material.
On a particular material. Yeah.
Yes, sir.
See, at IIT Kanpur, let me intervene. IIT Kanpur, we have been able to achieve surface finish, which I did not mention today,
Yes,
as
sir.
good as 0.5 nanometer, that is 5 angstrom. 5
Okay.
Dr. Prabhat Ranjan on silicon wafers. So
Okay.
depending upon the process that you are using and depending upon the finishing parameters.
And for example, yes,
Yeah.
sir. On your material, how long time it will take, sir, to get that 29 nanometer finishing? How long time it will take generally? For example, it is on titanium.
No. See, it is not the material, or you cannot say like this, the material time taken. See, you have to see various things. First thing
Okay,
is,
sir.
what is the initial condition of the workpiece material? What is the initial
Okay.
surface roughness? How is the complexity of the part? Because the
Okay.
process which I showed to you on MRF, where you are
Okay, sir.
removing it in a different way. If you are going to use the process which Dr. Ravi Shankar and others use as abrasive flow finishing process, you can
Yes, sir.
finish it very quickly. But when you
Okay.
are doing with MRF and other processes, they are going to take a lot of time because you are finishing a very small area continuously. So
Yes, sir.
depending upon the part, depending upon the machines available, and depending upon the finishing parameter,
Okay.
it will decide how much time you are going to take.
Okay. So one more question.
Yeah.
Is it required to finish entire component or only some specified locations?
You can do both ways, depending
Okay.
upon your requirement. You know, the way I showed to you one video, you
Okay,
can
sir.
finish certain areas of the component only. But if you are going to use abrasive flow finishing process or magnetorheological abrasive flow finishing process, then their whole part may have to be finished. You can do partially also, but you have to then use another technique.
Okay, sir. Sir, thank you so much, sir.
Welcome.
Thank you so much.
Thank you. Thank you. So any other people, please?
Hello, good evening, sir.
Good evening.
Yeah, go ahead.
This is Professor in Venkatachalapati Institute of Aeronautical Engineering, sir. So that inaugural session it is really excellent, sir. Hello.
Yes,
Yeah,
yes,
yeah,
please.
go ahead.
Sir, let me know for knee pain, what is the material to transfer and that for above aged people, what is the
Pardon?
material?
Pardon?
Knee plantation, sir. Knee pain.
Knee
The
implant,
people.
sir. He's asking knee implant, what is the material used?
No, see, we did not go into the details of
Can
material.
I answer, sir?
Yeah, you please go ahead.
Yeah. So to Venkatachalapati ji, see,
Yes,
there
sir. Yes, sir. Yeah.
commonly two materials will be normally used in orthopedic surgeries. Okay.
Yes, sir.
So, for example, there are commercially available materials. One is chromium cobalt iron, another one is titanium.
Titanium.
In Indian scenario, most of the people will use chromium cobalt. It's because of the reason that our BMR is very high compared to other people. Okay, so body mass index is there, BMI, BMR, some people will they say body mass ratio and other things. So
Yes,
for
sir.
example, if you are putting a knee implant, normally knee implant will be like a C shape, basically. It
Yes,
will be,
yes.
okay. So what will
Yes.
happen if your body weight is too much? What will happen? This will bend. Okay, so the
Okay.
surgery will fail. So the strength of chromium cobalt iron is slightly higher than titanium. That's why people will go for stainless steel based, or I mean to say chromium cobalt based. In otherwise, what will happen? There will be eccentric problems and other things that the people are nowadays facing. So I mean to say is that there are two varieties of material that you can use. One is titanium. If you are fit enough, or if the particular patient is fit enough and his body mass ratio is as per the standards. If the patient is oversized, or if your weight is too much high or something, because this
Yes,
load
sir.
will fall on your knees, because of that, people preferably they will use chromium cobalt iron, which is a non-corroding material as per the theory is concerned. But see, nothing in this world is uncorrodable again. Okay, so the answer for you is chromium cobalt iron and titanium.
Titanium. Very good. Thank you. Thank you, sir. For aged people also, they can, depending upon the weight, they have to
Irrespective of it is irrespective of any people.
any people.
So the normal age limit of that implants is around 16 to 20 years.
Okay, okay, okay.
Yeah, so for aged people, that normally it can go lifelong, but people, they say it is 20 years or slightly. Doctors say, see, it's a
Yes, sir.
terminology. Whenever the patient goes to the hospital, they first and foremost they say that survival chances is very less. Like that,
Yes, yes, sir.
so it will be like 20 years, like that they will say. But it is up to you how you are. See, for example, elderly people, if they are not at all walking or very minimal walking, so that 20
Yes,
years,
sir.
40 years or 50 years also.
Okay, okay.
It's how much you are walking. So because of that, relative motion will be there and other things.
Oh, right, right. Okay. Thank you. Thank you so much, sir. Right, right.
Thank you, sir. So yeah, any other people, please?
Sir, good evening, sir.
Yeah, please go ahead.
Sir, myself Kishore from Vijayawada, sir, good level engineering college. Sir, my question is, just I have seen that knee replacement using additive manufacturing for a specific patient development. So how can we take the dimensions for that specific patient? How can we develop that one for specific patient? New joy placement.
You have all kind of technology developed. See, X-ray and so many other things are there. With the help of which you can take the dimensions of the inside body. And depending upon that, you have to develop the implants. Because it cannot be just like the simple example I gave you, 8.5 shoe number, you don't have it, either 8 or 9. But all this is possible now with the help of additive manufacturing kind of technologies. You can develop exactly 8.35 or 8.5 if you know it well in advance. Definitely you have to know in advance that patient requires this size of the and this shape of the implant.
So people will use reverse engineering. Okay. So there is, whenever there is an accident or something, they will do CT scan. So from CT
Yes,
scan,
yes.
they automatically they can understand the, for example, if your one knee has to be replaced or one knee got injured or something. So other knee is also approximately same. So they can take the data from other knee. So CT scan images or micro CT scan images are there, from which the files can be taken for the 3D printing. So this they will do reverse engineering. I answered your question or any other further?
Sir, one more question, sir. Just now you told that chrome nickel is better used for the biomedical implants for like that. So is there any other better material than chrome nickel which gives a better mechanical properties as well as biological properties?
Titanium.
Titanium. So just you have told that strength with
Titanium
considering
strength
strength.
is less. Okay, so you have to compromise on that currently.
So we have to consider with body mass index.
Yes, yes.
It gives also better biological properties.
Yes, yes. It's a bio-inert material. Titanium is a bio-inert material. So it neither cause positives nor negatives. But however, that chromium cobalt, which consists of iron, so it may leach out Fe3 plus ions, which may cause you in the later the stage some problems to the other medical problems. So in case of titanium, the medical problems will not be there. So the better option is for you to maintain the BMI rightly before you go to operation.
Sir, can we detect the fracture before any other method to detect the fracture?
I'm not getting you. Can you repeat again?
Can we detect before the accident? Can we detect the future of the fracture? Is there any method to find the fracture of the particular bones?
Before the accident, you want to predict the fracture.
Yeah, yes, sir.
So people will use simulations, I think. I think Professor VK Jain.
No, I am not able to understand what you.
Sir, his question is before the accident, can we predict the fracture type and fracture
intensity? Predict the fracture time.
Fracture type of fracture and the fracture intensity, whether it is a severe or whether it is mild or like that. Before the.
No, I don't. I think he has to consult the doctor.
Normally, it is design people and simulation people will do some simulations. Like, for example, you see that car will go and crash, car test crash, they will do, no? In that one only, they will also do for the, what are the human effects, what will be the problems that they can encounter. That study, I think I am not the right person and we don't do that. But anyhow, you can do those things by simulations.
Yeah, okay.
So these are called crash analysis.
Yeah, okay, sir. Thank you, sir.
Thank you. So any other questions? We have already exceeded our time and so yeah, thank you. I think if you have any questions or something, so you can directly write to us or you can directly write to Professor VK Jain also. He is so kind that he will be normally reply you in a day normally. So normally, the experience that I have with Professor Jain is I will get the reply within few hours, but you may be not known that much, but you may get it in 24 hours. That much assurance I can give you. If not 48 hours, if he is traveling or something. Okay. So you can also
let me tell one thing. See, it is so highly interdisciplinary that one single person cannot be expert for everything, right?
Yes, sir.
One can be expert in the area of materials, another person can be in the area of machining or finishing, third person can be, in data analysis and so many other things. So this smart manufacturing will involve so many interdisciplinary areas to work together if you really want it to be a successful project.
Yeah. So with this, we are concluding the today's talk. So once again, I'm very grateful to Professor V.K. Jain. So we have a fond memories in terms of Hindi, in terms of.
So thank you very much.
I'm very thankful, sir, for your
Welcome.
valuable time. And I understand that we went more than 2 hours. So I always appreciate your energy. Thank you, sir, and thank you, participants. And tomorrow onwards, we will be starting at 7:30 again. Please be in time. So tomorrow we will have Professor Ram Kumar from IIT Kanpur, who is going to talk on bioimplants manufacturing and other things. Well, I have already shared the schedules by again Gandhinagar Harita. She is going to talk on ceramic implants and tribology, followed by the fourth person from Sri Chitra Tribunal Institute of Science and Technology, which is the DST Center and the best institute in biomedical from Trivandrum. So he is going to talk on bioprinting and bioink and other things, and then followed by Professor Vimal Katiyar, implants, how you place inside the body, how it will degrade inside the body and other things. And followed by the final talk from IAC Bangalore, Professor Bikramjit Basu. Currently, he is a DAD fellow. He's in Germany. We will connect to him from Germany or UK as per his schedule. Thank you, and please be on time. And another request for all of you is please mute yourself in between. When speaker is talking and your kids are talking or you are talking, it will be a confusing for the audience and other things. So respect the other people also. So again, on outset as a coordinator for this particular thing, and on behalf of me and my colleague Professor Kiran, I am very thankful to Professor V.K. Jain for his valuable time spending for IIT Tirupati. Thank you, sir, and thank you.
Welcome. Thank you. Good night.
Thank you. Convey my regards to Madam, sir. Yeah, thank you.
Okay. Good night.
Thank you, sir. I'm ending the session, sir. Thank you.
Okay.